Hello everyone. Previously we have learned about how we perform different operations on vectors that we have. We have looked at vector addition as well as vector subtraction. And in fact, we have discussed what are the different types of vector multiplications that there are, that is both dot product as well as cross product. And we have understood that considering dot product is what is significant for understanding different concepts that there are in machine learning as well as deep learning. That's the subject of our discussion in this particular session. So that is to learn about how you perform dot product of two different vectors that there are. All right. So before we get into discussing a little further about dot product of two vectors, let's understand that we were able to represent a particular vector v with respect to three different basis vectors, that is x hat, y hat, and z hat. So let's represent those three different basis vectors again. That is x hat, y hat, and z hat, all of which are perpendicular to each other and also have unit length or unit magnitude, isn't it? They are orthonormal vectors since they are both perpendicular to each other as well as having a unit length or unit magnitude. So now we have expressed this particular vector v, which is like 3 points away from origin on the lines of x-axis, and hence we have this 3 for x coordinate and the value of 2 for y coordinate, basically because it's 2 points away from the terminal point of this particular v vector is like 2 points away from origin on the lines of y-axis, and it's exactly 1 point away from origin on the lines of z-axis. You're not able to visualize it in 3D basically because the plane that I have been drawing here is represented in 2D. So you'll understand it better here. So I have expressed two different vectors, that is u and v here, and provided the different coordinates 2, 0 and 2, 1, 0 and 0 for u and v vectors. So this is your u vector. The u vector is 2 points away from origin, so 1 and 2. When you look at this terminal point for this particular u vector, it's 2 points away from origin. So similarly, your z, or probably your z coordinate, right? So this is your z axis and this is your x axis and this is your y axis. So your z coordinate basically also has got this particular value of 2. Again, it's 2 points away from origin. So the terminal point, when you observe what is the corresponding value on the z axis, you observe the value of 2 here. And you do not have any value at all for the y coordinate, that is 0. It's exactly located at this particular origin point and it does not bear any significance as such. Here you can represent your vector u in terms of ux, uy, and uz. This is a column vector wherein you have expressed ux, uy, and uz, which is coordinates on the lines of x-axis, y-axis, and z-axis. You also have understood that this particular vector is defined with respect to three different vectors, that is x hat, z hat, and y hat, right? So which are existing on the three different axes x, y, and z respectively. So if you change the basis vectors for your vector space, so obviously the coordinates also are going to get changed, and that's what we have learned. With a change in basis, you are absolutely going to have a different set of coordinates altogether. And hence we were able to express a vector v, which is defined with respect to three different basis vectors as vx x hat plus vy y hat plus vz z hat, isn't it? We also have looked at considering a column vector for expressing this particular vector in its component form. So this is a component form or component form representation of a particular vector v that's defined in a particular vector space, defined also by three different basis vectors x hat, y hat, and z hat, right? So similarly, you also can represent your vector u as ux x hat plus uy y hat plus uz z hat. Column vector with ux, uy, and uz, right? Now you are willing to find the dot product of these two vectors u and v. The dot product of these two different vectors u and v is given as ux vx plus uy vy plus uz and vz. We absolutely do not have any idea on how we have deduced this particular formula for the dot product of these two vectors that we have defined as u and v, isn't it? So this is your dot product. Don't worry, we are going to see how we have deduced this formula where u and v are expressed in its component forms. You also can define the dot product of two vectors u and v as the magnitude of vector u multiplied by the magnitude of vector v multiplied by cos theta, where theta is the angle separating between these two different vectors u and v that you have. All right, you can either express this in terms of ux vx plus uy vy plus uz vz, or magnitude of u multiplied by magnitude of vector v multiplied by cos theta. All right, this is what it's all about. You can consider this particular data that we have already created, that is vector 202 for u and vector 100 for v, and also try to calculate the dot product using this formula. So ux vx should be 2 multiplied by 1, that is 2. Uy vy should be 0 multiplied by 0, that is 0, plus again uz vz should be 2 multiplied by 0, that is again 0. So the resultant value of the dot product of two vectors u and v is basically a value of 2, which is again showed here. And this is how you calculate the dot product of two vectors. Now let's look at how you derive this particular formula for us to have a solid understanding about the dot product of two vectors. So we know that we are looking at finding the dot product of these two vectors. We also have expressed u as ux x hat plus uy y hat plus uz z hat, right? So let's substitute this particular equation in vector u here, that is ux x hat plus uy y hat plus uz z hat multiplied by vector v can be expressed as vx x hat plus vy y hat plus vz z hat. Now you have two different expressions here, that is on the left hand side and right hand side. So every single term on the left hand side expression needs to be multiplied by every other term that's present on the right hand side. And let's do that, and let's do that process till all the terms in the left hand side expression are exhausted. So you multiply this particular term here, this term here, with all the other terms that are present on the right hand side expression. So it should be ux vx multiplied by x hat plus ux vy multiplied by x hat y hat plus ux vz multiplied by x hat z hat. So the second term here should be uy multiplied by vx multiplied by y hat x hat plus uy vy multiplied by y hat plus uy vz multiplied by y hat z hat. And let's go for the third term here now. So it should be uz vx z hat x hat plus uz vy z hat y hat plus uz vz z hat z hat. Now we also have defined another formula for your dot product of two vectors, that is magnitude of vector u multiplied by magnitude of vector v multiplied by cos theta. That is the angle separating between both these vectors. Now let's consider these basis vectors x hat and x hat. So we know that all these basis vectors are separated by an angle of 90 degrees because they all are perpendicular to each other. This is x hat, y hat and z hat, right? So x hat multiplied by x hat. Let's say that you have a vector x hat and multiplied by the same vector x hat, which is lying on top of each other. It's nothing but the same vector, isn't it? So you are multiplying x hat by x hat. That means to say that the angle separating between those two vectors, that is the same vectors, will be 0. So your theta here is 0. So when theta is equal to 0, your cos theta is 1, isn't it? So of course your x hat multiplied by x hat will also result in a value of 1, basically because your magnitude of x hat multiplied by magnitude of x hat again multiplied by cos 0 would result in a value of 1 multiplied by 1 multiplied by 1, that is equivalent to 1. So x hat multiplied by x hat would result in a value of 1. So y hat multiplied by y hat will again result in a value of 1. Z hat multiplied by z hat will result in a value of 0. Whereas if you consider x hat and y hat multiplication, so they are separated by an angle of 90 degrees. So of course 1 multiplied by 1 multiplied by cos 90 is going to result in 0 because cos 90 is 0. All these terms gets cancelled out because of the value of 0 that these two multiplication of basis vectors would cause, right? All of these will result in a value of 0, and hence we are left with these terms 1, 2 and 3. right? So since the term within this inner parenthesis is evaluated to 1, so you can simply write this as ux vx plus uy vy multiplied by 1, which is again uy vy, plus uz vz multiplied by 1, which is again uz vz. And this is what we have been talking about, isn't it? And this is nothing but your dot product of two vectors u and v that you had. All right. But what about this particular formula? We are still unaware of how we have deduced this particular formula, that is multiplying the magnitudes of two different vectors that you have, also by cos theta, where theta is the angle separating between them. What about this? Okay, let's say that you have two different vectors, that is u and minus v here, for instance, and this is your u plus minus v, which again is nothing but vector u minus vector v, isn't it? There is an angle theta that's separating between u and minus v vectors that you have. So of course, law of cosines state that your c square, let's say that this is c, and let's call it as a and let's call it as b, right? The magnitude of each of these vectors that you have can be called as a, b, and c respectively, right? The law of cosine states that c square is equal to a square plus b square minus 2ab cos theta. All right. If you remember law of cosines from your 10th grade or probably +1 mathematics, so you understand that law of cosines is given by this. And that's how you also derive your hypotenuse value, right? So for instance, if this is a right angle triangle, this is a right angle triangle that you have, and this is your theta that we are talking about. So this is your theta that we are talking about, right? So your theta here is 90 degrees. Of course, this is your A and this is your B and this is your C. C is basically given by square root of a square plus b square. So let's substitute this particular value of theta in this particular law of cosines formula that we have. That is equal to a square plus b square minus 2ab multiplied by cos 90 is 0. Right? So that will result in a value of a square plus b square. And your value of c will be square root of a square plus b square. Nothing but the same thing, right? If at all your theta is not 90, if both these vectors a and b are not perpendicular to each other, then obviously it will be replaced by minus 2ab cos theta, isn't it? Now we have c being represented by u minus v, a being represented by vector u, and b being represented by vector v. So the magnitudes of this particular vector is given by magnitude of u, magnitude of v, and of course magnitude of u minus v. So let's substitute all of these in this particular law of cosines formula, which will be nothing but your u minus, sorry, it's nothing but u minus v whole square, right, is equal to u square plus v square minus 2 multiplied by modulus of u, that is nothing but the magnitude of u, magnitude of v, and cos theta. And this is what we are supposed to find, isn't it? And we have expressed the dot product of two vectors as magnitude of u multiplied by magnitude of v multiplied by cos theta, right? So let's keep this in left hand side and actually bring this particular left hand side expression to the right hand side. So that will eventually become magnitude of u multiplied by magnitude of v multiplied by cos theta is equal to u square plus v square minus u minus v whole square here divided by 2, right? Let's substitute whatever component form equations that you have for u and v. The component form equation would be ux x hat plus uy y hat plus uz z hat for vector u, and for vector v it should be vx x hat plus vy y hat plus vz z hat. Right? When you substitute all these equations into y and u and v respectively, then obviously this is going to converge to our expression ux vx plus uy vy plus uz vz. I'm not solving this completely. We can say that substitute vector u with this and vector v with vx x hat plus vy y hat plus vz z hat, right? So that's going to converge to this particular formula that we have already derived, and now we can state that your magnitude of vector u multiplied by magnitude of vector v cos theta is equivalent to ux vx plus uy vy plus uz vz. So there are two different formulas, basically because one is expressed in component form and the other one is not expressed in component form. That's all. And that's why we have two different formulas. Both are useful for multitude of reasons. Okay. I hope we have pretty much understood about how we perform dot product of two different vectors, and also how we derive the formulas for the dot products that we have already expressed. In the subsequent session, we are going to discuss briefly about the vector projection, what exactly is vector projection, and how we are going to calculate the vector projection that we can have in a given vector space. That's all in this particular session, and thanks for watching.